Hi everybody. We are going to go over 3 problems on page 23 of the logs packet. This is the last lecture video I'm going to do covering content from logs. After you get through these 3 example problems, you should be set up pretty well to complete the rest of the packet, solving the rest of the log equations, including the challenge problems, solving log inequalities, and then completing the review at the end of the packet, should you choose to do so if you want that extra practice. So there are 3 problems on page 23. I'm going to start with the first one, go all the way through the bottom, and we'll talk about how to solve log equations and determine if you have extraneous solutions. So let's take a look. On page 23, example 1a, we've got log base 3 of x plus log base 3 of x minus 6 equals 3. So you're asked to solve the log equation. This is actually going to require us to use what we know about the log properties. When I have the sum of 2 logs that have the same base, I know I can condense the expression down into a single log. So let's do that to start. I have log base 3 of the quantity x times x minus 6 equals 3. So addition of 2 logs with the same base becomes multiplication inside of a single log with that base. So right here, I've turned this equation into a single log, log base 3 of some quantity equals 3. This is awesome. We're ready to actually turn this into an exponential equation. So to do that, I'm going to take this base of 3, I'm going to raise it to this power of 3, and I'm going to set it equal to the entire inside of the log. It's great. I'm turning it into an exponential. And if I actually expand this out, 27 equals x squared minus 6x. This is starting to look like a quadratic. So let's keep this going. Let's get 0 on one side. 0 equals x squared minus 6x minus 27. I'm hoping that this is factorable. 0 equals x minus 9, x plus 3, and it looks like I'm getting 2 solutions, x equals 9 and x equals negative 3. So 2 potential solutions, but we have to figure out, is it possible that any of those are extraneous? And the thing about logs is, a natural log, a log base 10, or really any log, doesn't really matter what the base is, the quantity inside of the log cannot total out to be a negative number. So what I need to do anytime I'm solving a log equation is check at the end. I gotta plug back in. I gotta plug 9 in and see if any of my log terms end up with a negative inside. If I plug 9 in back here, that's okay. That's log base 3 of 9. And if I plug 9 back in here, 9 minus 6 is positive 3, and that's okay. So this is actually a viable solution. Right now, let's check out negative 3. When I plug negative 3 into the first log base 3 of negative 3, not allowed. In addition, if I plug negative 3 in here, log base 3 of what would be negative 9, that's kind of a double whammy, right? In both instances, I'm ending up with a negative value inside of a log, and that can't be evaluated. This is called an extraneous solution. We throw it out. One final solution, x equals 9. All right, so let's take it to our next example. Your next example is set up as an exponential to start. And there are a couple of different ways you can take it. Let me get the problem written down first. So we have 36 to the x equals 12 times 3 to the 2x. So this is set up as an exponential equation. And it's an exponential because I obviously don't see any logs, but also the variable I need to solve for is up in an exponent. It's actually showing up in 2 places. So anytime you're trying to solve an exponential equation and the variable is up in the exponent, a great thing to do is to take the log of both sides. So you actually have a choice. You can take the log of both sides, you can take the ln of both sides. It kind of doesn't really matter. You can sort of choose. Taking some log, be it the natural log, log base 10, log base whatever, you want to take a log of both sides. What you do to one side of the equation, you do to the other. So since it's a little bit shorter, let's just take the ln of both sides, the natural log. And it's shorter because it's literally writing 2 letters instead of 3. That's why I need shorter. So I'll take the ln of the left side, and I'll take the ln right side. Okay, right here, let's apply the power property. So I know that anytime I have an exponent or a power inside of a log, I can drop them in front as a multiplier or a leading coefficient. So that x drops down, this becomes x times ln of 36. And here, let's think back to our product property. When you have a product of two things, this is 12 times 3 to the 2x. A product inside a log, split it apart, turn it into a sum. This is going to be the ln of 12 plus the ln of 3 to the 2x. So that product of inside of a single log becomes the sum of two separate logs, or lns in this case, natural logs. Okay, again, I can see some power properties happening here. Why don't I take that 2x and pop it down in front? We've now done the product property here. We've taken that 2x, we've popped it down in front. It becomes a multiplier, a coefficient on the ln of 3. All right, so now let's think back to what we're even trying to do. We're trying to solve for x, right? X is showing up on the left, x is showing up on the right. We want to get anything that has x on the same side of the equation. So let's do this. Let's subtract 2x ln of 3 from both sides of the equation. These will cancel. Just keeping a balanced equation here. And so now I have x ln of 36 minus 2x ln of 3 equals just the ln of 12. Now, something to remember is that, like, the ln of 12, that's just a number. Similarly, the ln of 3 is just a number. The ln of 36 is just a number, all right? So we're really, we're sort of dealing with, exact values of numbers here. But now what I'm seeing on the left-hand side is that here's one term that has an x in it. Here's another term that has an x in it. I think it would be helpful for us if we pulled the x out of both terms. So if I take out that x, I'm left with the ln of 36 minus 2 times the ln of 3 equals the ln of 12. Okay. So, taking a look at what we have here, I've now factored out an x from both of those terms, right? And so I want to isolate x, I want to get it alone, and to do that, I could divide the entire side of this equation by that expression, because this is x times all of that stuff. So let's do it. Let's divide both sides of the equation by that long expression, and then we'll work to condense it. I'm going to divide the right-hand side by the same thing. These will cancel. And so now the x is all by itself, which is what we want to happen. So x equals, all right, now let's talk about what's happening on the right-hand side, particularly in the denominator. I am subtracting two logs that technically have the same base. This is a natural log, this is a natural log. The base is understood to be e on both of these. So something I can actually do is condense this down to be a single natural log, single ln, right? Before I do that, though, I want to consider this leading coefficient in front, this 2. I think I actually should take that 2 and pop it back up onto the 3 as an exponent. So I'm going to do reverse power property so that I can then condense them down into a single log. So here's what I have right now. I have the ln of 12 divided by the ln of 36 minus the ln of 3 squared, which is 9. Okay, now that I've gotten that leading coefficient back inside of the log, turned it into a power, I have subtraction of two logs with the same base, turn it into division inside of a single ln. So this is going to be x equals the ln of 12 over the ln of 36 divided by 9. All right, let's keep working with that. We know that 36 divided by 9 is 4. So this is going to be the ln of 12 over the ln of 4. And the last thing, when you're dividing two logs, in this case they're natural logs, when you're dividing two logs that have the same base, you can actually do reverse change of base property, and we can turn this into a single log where the base is 4 and the inside of the log is 12. So this will become log base 4 of 12. Now, you might be thinking, well, wait a minute, I saw lns here. How is it all of a sudden turning into log? Well, remember, ln, it is implied that that has a base of e. And I am trying to use change of base to turn this into a single log, right? A single log that has a base of 4, the thing in the denominator. And so it's inappropriate to use ln here. I need to be using log notation. It's log base 4 of 12. We just use change of base, and that's our final answer. And now if you pop that in your calculator, the log base 4 of 12, that comes out to be a positive value. And so when you think about it, I guess it actually doesn't really matter because our initial equation was an exponential. And so something to consider about exponentials is that exponential equations don't have domain restrictions. They have range restrictions. So I don't have to worry about my final answer here, whether it's positive or negative, because my initial equation was an exponential and there are no restrictions on x. When you do have to be concerned about final answers being extraneous is when your initial equation, the initial equation you're provided with, is a log equation. For example, what we saw in example 1, part A, the first equation we solved, that was a log equation. So we had to look for extraneous solutions at the end. Let's do one more, very bottom of page 23. So again, we're given an exponential for this one. 5 to the x equals 4 to the x plus 2. Okay, so this is an exponential. When I solve, I don't have to worry about extraneous solutions at the end, right? Because I don't see any logs in the initial equation. Okay, so solving for x, we can do basically what we did in the last problem, right? So you might be thinking, well, is there a way that I could get these bases to have a common base? But there's really no way to do that. Like 5 and 4, it's not like we can turn both of those into a base of 2 or base of 3. So instead, what we should do is take the log of both sides. You can take log base 10, you can take log base whatever. I'm going to do the ln of both sides because it's just easier to write. It's 2 letters instead of 3. I'm going to take the ln of 5 to the x and the ln of 4 to the x plus 2. What you do to one side, you do to the other. Power property. Drop it in front. X, ln of 5. Again, power property. X plus 2 times the ln of 4. Okay, so from here, remember, ln of 5, that's just a number, right? So this is some number times x. And likewise here, ln of 4 is just a number. So I have some number times x plus 2. So what I should do here is distribute. Distribute that number into the parentheses. So the left-hand side will be unchanged for now, x ln of 5, but the right is going to become x ln 4 plus 2 ln 4. So it's just distribution. Okay, now we're trying to solve for x. That means get anything that has x in it on the same side of the equation. So right here, I should be subtracting x ln 4 from both sides. Those cancel. Okay, so here I have x ln 5 minus x ln 4 equals 2 ln 4 on the right. Both of the terms on the left-hand side have x in them. So let's factor it out. This becomes x times ln 5 minus ln 4. And on the right, 2 ln 4. Okay, well right here, we are subtracting two natural logs. We're subtracting two logs that have the same base. And when that happens, you can condense it to a single log. So this is going to become x ln of 5 over 4. 5 over 4, that's a positive number. I'm allowed to have that value inside of a log. Equals. Something we should do here, we're going to change this again with the reverse power property. We're going to take that 2 right there, and we're going to bring it back into the log. So we're going to bring it back in, and we're going to make it 4 squared, reverse power property. So 4 squared becomes 16. So we're getting there. I'm trying to solve for x. I want to get it by itself. So I'm going to divide both sides by ln of 5/4. These will cancel. And now I've got x equals ln of 16 over ln of 5/4. And again, when you are dividing two logs that have the same base, in this case natural logs, they're longs, they both have base e, we can do the change of base property. The change of base property says this can become a single log. A single log where the base is the quantity in the denominator and the inside of the log is from the numerator. So this will become the log base 5/4 of 16. And again, these were natural logs, but once I use change of base and the base becomes something other than e, my notation needs to change to log. So log 5/4 of 16. If you pop that in your calculator, again, that's going to be a positive value. But it doesn't matter if that's a positive value or a negative value or 0, because when we go back to our initial equation, it's an exponential equation, and I don't have to worry about domain restrictions. So there aren't any extraneous solutions to worry about. That's our final answer there. All right. I hope this video was helpful to you guys. You now have enough information to finish the rest of the packet. Let me know if you need any additional help. I've got this awesome whiteboard. Happy to provide help through Zoom, Schoology, whatever you need. Let me know. All right. Have a good night, guys. Bye.